Today we're going to look at what's called conic sections, or basically sections of a cone. Now, conic sections can be described in many different ways. We'll look at a few of those ways. The ancient Greeks studied the geometric properties of the conic sections, describing each in terms of the intersection of a plane and a double-napped cone, as we see in the illustration here. If we take a plane and intersect the cone horizontally, we get a circle. If we slant the plane a little bit and go through two of the sides of the cone, we get the ellipse. Now, if we take the plane and one side goes, the plane goes through one side and then out the top, we get what's called the parabola. And finally, a vertical plane slicing the double-napped cone, we get this hyperbola. Now, there's some other results that happen if the plane slices the cone in just the right place. And in fact, if the plane intersects the cone at the vertex, the very point of the cone, we end up with what's called degenerate conics. Here are the illustrations. We end up with a horizontal plane right through the center, right through the vertex. We get just a single point. If the plane lines up just right on the edge of the cone, we get this line, and then a vertical plane slicing through exactly through the vertex, we get two intersecting lines. Now, while the Greeks studied the geometric properties of the conic sections, later on in the history of mathematics, the conic sections were studied algebraically, and it was generalized that all of the conic sections would fit into the form of this general second-degree equation: ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, where our capital letters A, B, C, D, E, and F are all real numbers, coefficients of the variables x and y. Now, we will not focus on anything dealing with the xy part. Our study of conic sections will be limited to where b equals 0, and then the other combinations will lead us to one of the conic sections we talked about earlier. But one particular equation that we use a lot actually turns out to be a conic section, although we've never defined it that way. Think about the function y equals 1 over x. And the graph of it, well, we have a vertical asymptote at x equals 0, horizontal asymptote at y equals 0, and we get, well, if I could draw, well, that's at least a little bit better, but anyway, this graph is fairly familiar to us, and if we would rewrite the equation, let's multiply x on both sides of the equation. We get xy equals 1, and then subtract 1 from both sides. We actually see the form of our general second degree equation. B equals 1, and f would be negative 1, and all the other coefficients would be 0. Anytime we have the xy term, we're going to get a rotation on our conic section. Now, this conic section actually is a hyperbola that has been rotated 45 degrees. And as we study the properties of the hyperbola, you'll see how this fits into the form of the hyperbola. But we've actually been working with hyperbolas before in this form. We just never said anything about it. Plus, it's a special case for a hyperbola being rotated. What we're going to focus on in describing the conics is a definition of a locus or collection of points, and we will be defining each one of these conic sections by way of one point compared to another point, and then developing the general equation of each of the conic sections. We have seen the definition of a circle as a locus of points, and that definition again is all points xy in a plane that are equidistant from a fixed point hk. Now we define that distance as the radius, and that fixed point hk represents the center of the circle. So as we look at the graph of this circle, we have all of these points on the circle, and in general we call them xy. Might be 2, 1, might be 0, -4, something like that. But because we're defining it as the distance, we can take the distance from hk out to any of these points here on the circle. And because of the distance formula, we can set up an equation. R is going to equal x minus h quantity squared plus y minus k quantity squared. And that's an equation representing all of the points that match this description. Now we usually make this equation a little easier, saying the standard equation is the square of both sides. We say r squared equals x minus h quantity squared plus y minus k quantity squared, and we use this as the equation for our circle. With this in mind, this is how we will describe and examine the parabola, the ellipse, and the hyperbola in other videos.